and it's on wave-induced flexure of multiple ice shelves. Okay, so please start.
Everyone, yeah, thanks for having me for this MOSI conference. Yeah, so today I will talk about the wave-induced flexure of multiple ice shelves. So I want to start with the ocean surface waves impacts on the ice shelf. So recently we have some observations caught up that ocean waves can impact the ice shelves and affect the stability of the ice shelves. And as a picture, as you can see from the left hand side, you see my mouse, right? Mouse cursor. Yeah. So
Yes, we
for
can
the
see it
left,
clearly.
okay, good. Yeah. For the left figures, you can see. So this is a Larsen-B carving, or actually it's like disintegrate right now. So this is happening in back in 2002. And this is recently. This is because of the interaction between the swells and the shelf front of the Larsen-B. And on the right hand side, you can see this is a Sulzberg carving, and this is back on 2011. And this is because of the tsunami waves induced by the Hongsan Japan 2011 earthquake. So we can say there are a lot of observations of ocean waves can impact the ice shelves. So recently, scientists and mathematicians they trying to deliver some models to models to have a to analyzing how the ocean waves can how the interaction between ocean waves and ice shelf. And usually, and this is one of the examples. So mathematical models they have ocean waves come in and they model the ice shelf flexure as like a elastic steam plate, and they couple with the water motion, and the water motion is modeled as a linear potential flow. And recently now we have been validate our model result with the measurement they conducted in the Ross ice shelf. And first I want to begin with that first. And just to be clear, where is Antarctica? Okay, so this is a map of Antarctica, and you can see a lot of ice shelves around Antarctica, right, around the coastline. And the Ross ice shelf is the one being studied most because his is one of the largest in area around Antarctica. Okay, and just to share, so Ross ice shelf is right around here. Okay, yeah. And so back in 2012 or 2014, there are a lot of measurements has been conducted on site to measure the ocean waves, to measure the ice shelf, so Ross ice shelf from deflections due to the ocean waves, and and the results are looking like this. Okay, so this is figures where the y-axis is the displacement in shelf against the displacement in ocean. So this is more like a ratio between these two. And the x-axis is the wave period. And you can see wave period, we can categorize them into three different regions. So one is called swell. So swell is usually around 10 seconds to 30 seconds. So it's really short period wave. And then it's in between, you have a 10 seconds, from 30 seconds to 300 seconds. So that's infragravity wave. And then you have a very long period wave called tsunami at the end. So that's over 300 periods, 300-second period. Okay. And then you can look at this one here. So first you can look at the blue one. So the blue one is the one from the measurement. Okay. So they actually conduct some measurements around the Ross ice shelf, and they measure the displacement in the shelf against the displacement in the ocean. And the blue one is from the measurement, taken from the measurement. And the blue, oh, sorry, my bad. So the black one is taken from the measurement. And then the blue one is taken from our models. And you can see our model is quite closer to the measured average. So that's really good. And then what we did is we put our model, so we select a study region, which is around 500 kilometers around the coastline and 300 kilometers into the shelf. So we're trying to analyze how the different geometries of the Ross ice shelf are affected by the ocean waves. And we choosing and here are the results here. So first we had the top two panels are the geometry maps. So you have thickness distribution and cavity depth distribution. And you can see there are some. So first of all, you can see for the thickness map there are some crevasse or some rifts around the Ross Ice Shelf, particularly on the highlight text circle text here. And then the bottom two panels are the result from different ocean waves. So left bottom is the swells. So and with a peak period of 30 seconds. Okay. And the right hand side is the IG waves for the peak period of around 67 seconds. And you can see the outlines of those highlight package here are first have some correlations between for the result and the geometries. Okay, yeah. And so what we're trying to then analyzing is so we know there's a relationship between thickness, cavity depth, and with the flexure strain. So what is actually the relationship? So that's what we're trying to investigate. Then what we have done now is extending our analysis to another ice shelf. And this case, we did for Larsen ice shelf, as you can see from the map. So it's in the left top corner here. The reason we're using Larsen C ice shelf is because this is the one that is one of the largest around the Antarctic of Pennsylvania, right? And that's the area where most is interact most with global warming and sort of thing here. So we want to investigate this particular shelf first. Okay, so what I have done is, sorry, second. Yeah. So what we have done is, okay, let's zoom into this ice shelf. So as right hand, you can see this is Larsen C ice shelf. And we're passing through a transect. Okay, so transect is the line, right? And as you can see, it's the blue line here. So we're passing through a transect into the Larsen C, and we obtained a realistic geometry from the transect, and this is obtained from the BAMAP2 data set. All right, yeah. And you can see, and we're using H as our cavity depth, and D is the shelf thickness. And because this is a realistic geometry, so it's gonna vary along the location. So we use DX and HX. All right, that's good. And then so our investigation is trying to analyzing how this variant geometry is gonna affect the shelf's flexure strain. And I want to point out there are some features around this particular profile. So you can see for this particular profile, we have some variation in the thickness, and this is due to the crevasse or some building melting, right, around the drafts of the ice shelf. And then we have some really shallow or small cavity depths in the middle between 80 to 100 kilometers. And at the end, we have a really large cavity depth and thick and really thick ice shelf, right? So I want you to memorize these three unique features because I'm gonna point out them later on. Okay. All right. So first, what I'm trying to do is I want to eliminating all the variation of the geometry features one by one. Okay. So first of all, I had a realistic profile like this, and then I want to first eliminating the draft effect for the geometry. So what I have done is I put into a uniform draft, and then because I want to keep everything else the same, so that's why this profile looks like unrealistic. Okay, but this is just for the investigations. Okay, yeah, don't worry too much about the realistic here. Okay, so we put a uniform draft here, And because we want to keep the thickness the same as before, so you can see there's much of ice on top of the water. Okay, but the whole point here is keep the draft uniform and everything else is the same, right? Same as a realistic geometry. Okay, so this is the first change we have made, and then we made another change based on this one. So we now keep the thickness the same, right? So now the draft and the thickness they both the same. Now the only thing different is the seabed now. Okay, seabed. Okay, so this is the second step we have done, and the last step we have done is now okay. What if we completely change everything to uniform? Okay, so this is the last step. So now we change everything to uniform. So now also so just recall what we have done here. So first we change the draft, then we change the thickness, then lastly we change the seabed. Okay, so now what I'm trying to do is I feed different period waves into different geometries and see how they're different from each other. Okay, and I did that with 3 period waves. So one is 10 seconds, one is 150, one is 500 seconds. And I choose these three wave periods because they are from different 3 regions, as I mentioned before. Okay, I want to say how they act differently for different wave periods. And just to mention here, the output here I used is the eta. So eta is denoted as the ice shelf vertical displacement, and eta second derivative of eta is proportional to the flexure strain. So I'm using second derivative of eta as my output. All right. Okay. So now, as that has been said, so what I'm trying to do is do some comparison, right? So let's just have a look at what I've been shown here. So first I start with 10 seconds. So yeah, so first I want to mention out what has been shown here. So you can see this is, so as I said, the output here is eta second derivative and against the location X, okay? Yeah, against location X, oh sorry, yeah, against location X. And then we have 4 different profiles, right? So one is realistic, one is uniform draft, one is uniform draft and thickness, and the last one is all uniform. So the first two, so the blue and orange are the ones that has same thickness but different draft. Okay, so realistic profile and uniform draft, they have the same thickness but different draft. So these two, you can say they are align each other, right? So the blue one and orange one, they are align each other perfectly. And then the last two is uniform draft thickness and uniform draft thickness and seabed. And these two will have same thickness as well, because they have the same uniform thickness in this case. Okay. So what really changes here? So the dominant factor here is the thickness. Okay. If you now pick up the blue one and the yellow one, you will see the blue one and the yellow one, what changes? So the blue one, no, we not do the, let's do the uniform draft and thickness. Okay, let's do the origin one and the yellow one. So the origin one and the yellow one, you can see the differences is the thickness, right? They both have uniform draft, they both have the seabed, but the only thing changes is the thickness. And and it shows a really different result from the uniform thickness and the varying thickness. Okay, so what I'm trying to say is the thickness is the dominant factor when it's in the swell region. Okay. Also, and do you still remember the 3 different some features from the ice shelf I mentioned earlier? So here are something I want to is really interesting. So for the first one here, you can see the first package here. This is where you see for the realistic geometries, you see a lot of crevasse and a lot of changes in the bottom of the ice, right? And that resulting into variations in the flexure strength here. And then we have a really thick ice at the end, right? you see for the geometry, we had really thick ice at the end, and that also result in reducing the flexure strength significantly. Right, so they all related to the thickness variations. Right, and now we move on to the IG waves, or you can say infragravity waves, and I pick a T 150 seconds. And in this case, it's the there are a lot of things going on here. So what I really want you to focus on is the orange one and the yellow one. Okay, so so you can say orange one and the yellow one again. As I said, orange one and yellow one, the only difference is the thickness. Okay, so thickness, so thickness is the difference, and you can see these two are now apart away from each other. Okay, so that indicates thickness also is still taking effect in IG waves, but not only thickness is taking effect now, but also the seabed is now has an effect into the result. Why? Because if you say the this one, so this is a uniform seabed, and the yellow one, so everything is the same, but without so that's the only variation is the seabed, right? So this one you had a seabed variation. Sorry, seabed variation here. So you have seabed variation here. So these two have a different seabed variation. That's the only difference, and you can see that definitely shows the differences in the result, right? So this one is much different to the uniform now. So what I'm trying to say is that seabed now is has an effect into the IG wave. Okay, and you also let me just clear everything first. Then you can see, first of all, for the first package here, we still have a lot of variations, and that is due to the thickness, right? So we have seen this from previous figure, and now this part is coming up because this is part where we have a smaller cavity depth, right? So we didn't really see this coming up for the swells, right? But yeah, because in that time the seabed and cavity depth is not really taking effect into the swell. But now we have a longer wave, so the seabed variation and the cavity depths are now actually has an impact on the result. Okay, so that's why you can see a lot of variation here. And lastly, we can see this one here, and that's due to the thickening of the ice and shallowing and the large cavity depths. Okay, so that's for the IG waves. And now what about really, really long period waves, like tsunami waves, right? So let's say we had a 500 period waves. And in this case now, you can say, okay, good. So what's going on here? So so now these two are actually close to each other, right? Before we said they are, so from the swell, they're really away from each other. Now for very large period waves, they're really actually almost equal each other now, right? Really close to each other. And you can say, so okay, so the differences between these two are the thickness. So this is the indication that thickness now is not really affecting the result compared to the swells and IG wave, right? Because you can say, even though thickness are changing, the result for these two has a marginal difference, right? Okay, so what happened? So why this one has a really large difference than the others? That is because you still recall that we have a really smaller cavity depth for the release geometry, and that's why so what I'm trying to say is, so that's why for really long period wave like tsunamis, so the cavity depth will be the dominant effect, right? Will be the dominant factor to have a larger strength. Then and it will determining so it will determine how large the strength is. So smaller cavity depth means larger strength, and and so that's it for this case study. So but this is only for one single transect, right? So maybe maybe that's just a coincidence, right? So what if you extend it to like study region, like a 2D area, right? So this is just for single line. Do you still remember? So this is for only one transect, one line. So what if we're doing this for a study region, like a 2D area? Okay, so this is what I have done. So I choose this particular area. So 140 kilometers across the coastline and 200 kilometers into the ice shelf, and choose this study region to analyzing how the geometries affect with the ocean wave with the waves. Okay. So what I have done is, again, I'm using 3 different periods. So 10 second, 150, and 500. I still keep this 3 period. And now, and I also plot some of the outlines for the strain, right? So some extreme values, like maximum values, onto the map. And I forgot to mention that. So the left-hand side is a thickness map, and the right-hand side is a cavity depth maps. Okay. And so let's first look at the 10 seconds. So 10 seconds is where you see the blue dot. All right, blue points. Okay. So that you can see a lot of maximum value are occurred around here, right? Around here. And this is where you have a really thin pack of ice around the shelf front. Okay. And yeah, some of them around here, and that is really due to the thinner ice as well. Okay, so what I'm trying to say is, so the 10 second is associated with the thinner ice, and then we have 150 seconds. So 150 second is a green one. Yeah, so green one is a combination of both. So the thickness and the cavity depth, they both has an effect in for the IG wave. And so that's why you can say
just reminding you that you've got 5 minutes left. Okay.
okay, yeah, I'm about finished soon. Yeah. Okay. Yeah, and so that's why you can see a lot of things here, and some of them is a grounding line here as well. Okay. And then we go into the 500 seconds. So 500 seconds is where the cavity depth is most important, right? So that's why now let's look at the cavity depth map. So you can see for smaller cavity depths, the outlines occur here and here. Yeah. So this is the indication. Okay, so that's why cavity depth and thickness has a different impact for a different wave period. All right, let me just clear up this. All right, then I plotted the median of the Larsen C against the wave period, and this is what I got. Okay, and we have so you can see the results increases with the swell in the swell region and reaches to maximum around IG waves, and it starts to decreasing for tsunamis. Okay, so this is similar to what we have seen for the Ross ice shelf as well. So that's really good. And then what I did is I did this for different other ice shelf, and yeah, so these are the 2 I have studied, and I did for another 13 ice shelf. And I want to point out is Wilkins and Congers are the ones that have a really large strength for swells, because they have a really thin ice, like really like around only 10 to 50 meters of ice thickness. Yeah, so that's why they have a really large strength over there, and they are the ones that have been disappeared or disintegrated recently. And lastly, I want to talk about is how the ocean. Yeah. So then I put the median of the strain for each ice shelf against the thickness, and particularly in this case is shelf front thickness, because shelf front is most interacted with the wave, and so I put it against the shelf front thickness, and you can see there's a strong relationship between the thickness and the shelf flexure strain for short period waves. On the other hand, for very long period waves like tsunamis, the cavity depth will be the one that has a strong elective impact for the shelf flexure strain. And yes, that's it for my, and in summary, yeah, that's it. And thanks for listening. Thank you.
Thank you very much, Jie. Yeah, sorry, you kept well to time. We've got some time for some questions here. So, Susan, would you like to ask a question? We can't hear you, Susan. You're muted.
Thank you for your presentation. In your realistic model, that vertical edge of ice sheet is uniform, right? For every case?
Yeah. This one?
Yeah, vertical edge of ice sheet in your realistic model. Yeah, go back.
The first one.
Yeah, everywhere that vertical edge is uniform.
No, they are not uniform.
No, if you got the edge, left side. No.
Yeah.
Next one.
Sorry.
I just like in your not this one. That red circular marking.
Circular. This one?
No, red circular marking. Yeah.
Do you know the page number, Susan? Is it forward or back in the
six, slide number 6.
Number 6.
This one?
No, not this one. 7. Yeah, here. If you go dx, that vertical edge on the left, ice water interface, that is uniform in every case.
You mean this one here?
Yes, that edge, that vertical edge, this edge.
Oh, you mean this?
No.
Okay.
Vertical edge at the interface.
I'll try and mark it myself. This edge here. This line here.
Yes. That is vertical line.
Okay.
It is uniform.
Oh, sorry. Yeah.
Okay.
You mean this one here?
Yeah.
Oh.
Yeah.
And under this situation, your realistic case and all uniform case got similar results.
Yes. So yes, exactly. So what I'm using is I'm using the shelf front values as my study case. Yes. Okay. I think I got what it is. So yeah. So what I have done is I'm using all the values from the shelf front. Yeah. So I keep the shelf front the same, and I change it so uniform value based on the shelf front values. Yeah, exactly. So that's what I have done here. Sorry, I didn't really.
How do you model that ice sheet? It's a thick ice model or thin ice model?
Yeah, that was my question. What, you never told us the mathematical equation you're using.
Yes, so the mathematical the thing I'm using is exactly the same as I have been using for the Nick Bennett's and Mike's papers here. So yeah, and I did. So this is more like a statistic analysis. So I didn't want to go in deep to the model.
It's a elastic thin plate, potential flow. Yeah. And you have like a multi-mode method or something like that. Is that right?
Yes, we have a multi-mode. Yeah, so we have a multi-modes for the.
And what happens at the end? At the end, the water the energy flows out at the end.
So yeah, exactly. So for at the end of the shelf, so we assume we're gonna have the semi-infinite condition. So it will flow out of the shelf instead of bouncing back. So there's no reflections. Yes.
Yeah. And so that's important, I think. Yeah, it's good to state that, because the ones that have it bouncing back creates a strong resonance effect.
Yeah, exactly. Yeah. So we try to avoid that in this case.
Yeah. And we don't see that. Yeah. All right. Yeah. I think we've run to the end of the time of the session. So I would at least take myself to thank Jie and all the